Good morning to all. I am Kishor from Bangalore Institute of Technology. Today I am going to explain my project on mass cause event training and inferencing. So before learning the training and inferencing of mass Gaussian, we want to know what is mass Gaussian. So mass Gaussian is nothing but an intrinsic segmentation algorithm. So what is segmentation? So segmentation is nothing but the pixel-based pixel classification where you will be focusing on the exact location of the object. The difference between object detection and object segmentation is that in object detection, the object will be detected with the background classes. So these are all the background classes with the background classes. This bounding boxes was detected. So this also background classes. These are also background classes. These background classes are unwanted classes. But in object segmentation, you will be getting the exact location of the object. So see here, you will be getting the exact location of the object by using the masking concept. So you can get this exact location. Background classes are not detected. So mass Gaussian was developed in the year of 2017 by the Facebook research AI team. It is an extension of a fast Gaussian. To learn about mass Gaussian, you want to know a little bit about the fast Gaussian. So I will tell you the little bit of fast Gaussian. So fast tossing backbone is a BGG 16 layer where you'll be having an 16 down sample or 16 layers. From that, the feature map will be passed to a region proportional network, where in a region proportional network, you'll be performing three cascade convolution and one constant convolution. For each grid, you will be allocating an eight. For each grid, you will be allocating an nine bounding boxes with the different scales 1 is to 1, 1 is to 2 is to 1, with different ratio 124 to 228 and 512 with different ratio you will be allocating, and that that anchor boxes will be passed to one layers for regression and the classification, and you will be performing some non-maximal separation, and that proposals will be sending to ROI pooling. So total 20k bounding boxes will be generated, and you will be refining the bounding boxes, and 2K bounding boxes, 2K proposals will be sending to the ROI layer. The main use case of ROI layer is to convert the proposal into a fixed size feature map. Now these proposals and this feature map will be concatenated and will be sending. ROI pooling will be converting this feature maps into a fixed size feature map, because the fully connected next layer will be the fully connected layer. Fully connected layer accept only the feature maps in a fixed layer because of the concept of weights in that fully connected layer. So ROI pooling layer will be doing some quantization, and it will be applying some max pooling, and it will be converting that to a 7 cross 7 or some 7 cross, mainly 7 cross 7 fixed size feature map, and it will be sending to that fully connected layer. Fully connected layer will be having the classification and the detection will be happening. So this is the fast CNN, and it uses the smooth L1 loss for the regression and cross entropy loss for the classification. So these are about the fast transition. The main change that they have made in the mass car CNN is that changing the ROI pooling layer, because of because of the quantization approach. They saw that accuracy has been decreased from 4 to 6% because there will be loss of so much of features. So to solve this, they introduced the concept of ROI align layer. So in ROI align layer, there won't be any quantization. They will be using some random interpretation, and they will be finding the exact size of the pooling layer, and they will be doing that. So they will be getting only generating the new features. They will not be losing the features. By this, they was able to see the accuracy increase of 5 to 6% accuracy increase. They was able to see from the ROI align layer, and there will be a skip connection from this before this ROI align layer, and it will be that skip connected feature maps will be sent to the fully convolution network. So this is the fully connected convolution network, and there will be some upsampling layers, and it will be detecting the masks. Then the feature maps that comes out of the ROI online layer will be sent to the fully connected layers, and you will be having the classification and the bounding box predictions. So this is an overview of the mask RCN architecture. Next, we'll be seeing loss function. So loss function will be the combination of loss function of class plus loss function of box plus loss function of mask. So ROI align layer, they will be using for the random. This is the random interpretation point, and they will be able to find this exact location. Why the quantization approach was happening? Because this will be your pooling layer. This is 2 cross 2 or 3 cross 3 pooling layer is there. So it is dividing the grid into half. So you will not be able to find this value. So you'll be quantizing, and you will be reducing till here, and you will be finding this fixed size. So these features will be lost. These features will be lost by this pooling layer. So the accuracy has been decreased. But align will be finding the exact point, this point, and it will be generating the new features. There won't be any quantization taken place. Next, so this will be the architecture of mass car CNN. The backbone network is the ResNet. ResNet uses the skip connection technique to reconsider the features. Then you'll be having the feature permitted. So what is feature permitted network? If you take a network, first it will be you'll be having a backbone. You'll be having a backbone network. You'll be having a neck network. You'll be having a classification network. So here the backbone network was the ResNet. The neck network was a feature primary network. So the net network or the feature primary network is used to reconsider the features that has not been considered in the previous layer. If some important features has been lost as you are downsampling, if some important features has been lost here, you cannot reconsider these features. So they have introduced this feature permit network where you'll be going bottom to top, again a top to down, again there is some concatenation, additional concatenation is taking place, and you'll be having the result here. So this from this layer you'll be able to reconsider these features. They are also introduced a BiFPN layer. In YOLO V4 they will be using an BiFPN, and efficient date they will be using a BiFPN, which is more robust than this, where they will be assigning a weights to this layer, and only the important features that the network fields can be extracted by from this layer to this layer by the network itself. So here all the feature maps will be concatenated, but in that BiFPN network, only the features which the network feels that is it is important will be concatenated. So that is the advantages of BiFPN. That is the extension of feature permit network. The extension of feature permit network was the PAN path aggregation network. The extension of path aggregation network was the BiFPN network. Okay, this is the feature permit network. Next, this will be ultra-spatial pooling. So what is ultra-spatial pooling? So ultra-spatial pooling is nothing but you will be able to get the, for example, you'll be able to get, this is a 3 cross 3 convolution layer. Now, if you want a 5 cross 5 convolution layer, you will be increasing the size. If we increase the 5 cross 3 cross into 5 cross 5 convolution layer, total number of parameters will be increasing. That is output size into input size into kernel height into width, plus 1 will be the total number of parameters. Plus 1 is for the bias. So total number of parameters for 5 cross 5 will be confirmed to be increasing than the 3 cross 3. So they have thought that why we want to use the 5 cross 5, why we cannot use 3 cross 3 and we cannot get the same receptive field as the 5 cross 5. As the neighboring pixel, they came to the conclusion that as the neighboring pixels gives the same information as the neighboring ones, why we want to consider the neighboring pixels? Why we cannot remove that neighboring pixels? That is how the whole algorithm. Why we need this neighboring pixels? This pixel also going to give same information. This pixel also going to give same information. So they have removed this neighboring pixels, and they was able to get a 5 cross 5 receptive field by using a 3 cross 3 filter. This is rate of 1, you'll be having 3 cross 3 filter. At rate of 2, you'll be having 2 holes. And you'll be seeing that you'll be able to get a 5 cross 5 receptive fields here. 1, 2, 3, 4, 5. So 5 cross 5 receptive field you'll be able to, this is rate 6, but it should be rate 2. If it is rate 2, it will be 5 cross 5. Rate 3, it will be if it rate 3, it will be 7 cross 7. Either it will be 13 cross 13. It will be increasing like that. So you'll be by using 3 cross 3, you'll be able to increase the receptive field size. By this, you'll be able to able to able to consider the increase the space, able to focus more on the spatial information by using the less parameters and increasing the speed of the network. So this is a spatial permit pooling layer network. Spatial permit pooling layer, not spatial, ultra spatial permit pooling layer. It is not a spatial permit pooling, it is ultra spatial permit pooling layer. Next, the result from this FPN will be passed on, it will be passed to ultra spatial permit pooling. The 3 cross 3 convolution has been applied. Why they are applying 3 cross 3 convolution? Because they will be doing some upsampling. To remove this upsampling effect, they will be producing a 3 cross 3 convolution network. Here they will be having an 1 cross 1, 1 cross 1, 1 cross 1 layer for the, because they'll be doing the addition of this layer on this upsampled layer. So the depth of the network must be same, the channels must be same. So they will be using the 1 cross 1 network. They'll be giving a fixed size channels or a same size channels. If it is 224, If this layer has 225 channels, so they'll be converting this also 225 channels, and they will be doing the addition. And to increase the non-linearity also, we can have the one cross one convolution layer. So next, the result from it will be going here. Then you'll be doing some upsampling. Then to 8x upsampling, 8x upsampling, you'll be able to get this result field size. Then 4x, 2x upsampling, you'll be doing a concatenation, and this concatenated result will be sent to the RPN network. That is a region proportional network, and from that you'll be getting the proposals. Then the proposals will be sent to the RY align layer. Then from RY align layer, and will be sent through fully convolution layer, and you'll be getting the detections classification on the masks. So this is the architecture of mask RCN, ORV architecture of mask RCN. So main thing, you are having ResNet, future neck network has a future plumbing network, ultra spatial fooling for to increase the accuracy and to focus on more higher receptive field by using the lower convolution size. And the fourth one is the concatenation. Fourth one is the upsampling and concatenation, and you'll be having the RPN and the predictions. So that's all about the mass Gaussian architecture. And last functionality we have seen. Next, we will be seeing the experimental results of the mass Gaussian, that the accuracy of mass Gaussian. So mass Gaussian with an average precision of, it was having about 62.3 with the IOE of 50%. Next, average, mean average precision of 43.4 with an IOE of 75. So by this you can say that as the IOE is getting on increasing, your mean average precision is getting decreased. So it is having a good mean average precision of 62.3, which is a very good mean average precision for a segmentation task. 43.6, it's also better as driver is getting increased. Next, summary. So the summary advantages is that it is high speed algorithm. So mass Gaussian is a high speed, and it is having high accuracy and easy to use, and a simple. It is a simple and intuitive. So the Facebook research have also implemented this Maskassin in a PyTorch in a framework named Reducton 2. They have Reducton 2. They have implemented this uh, mask Arsian. I will be showing that. So Reducton 2 CP Reducton 2 model zoo. So you'll be able to see the mask RCNN. Reducton 2 model G. So this is the Reducton 2 model zoo, where you'll be having all the pre-trained network. Coco instance segmentation based on mask Gaussian. So you will be able to see ResNet 50 with the future primary network, with the future primary network with the DC5, ResNet 50 C4, and you will see that they are also introduced learning at 1x faster, 3x faster, 4x, 3x faster. So it will be 1x faster learning rate, 3x faster learning rate. So it will be, this network will be much faster. Then you are having an mask average precision, box average precision. You can download this model and you can use this model for the inferencing, or you can again retrain this model. Inference speed also you will be able to see. So the main thing that Reducton 2 has been done is it has not has the fixed size learning rate. So they have used an 1x, 3x higher learning rate, so that your model will be much speeder, much faster than the TFOD, that is a TensorFlow Object Detection Framework. And it is a better than TensorFlow Object Detection Framework. Delta 2 is much better than the TensorFlow Object Detection Framework. The implementation thing that they have made is much better than the TensorFlow Object Detection Framework. On the logs, you can see when the training was much intuitive in the Delta 2. So next we will be, now we have seen about the architecture of overview architecture of mass Gaussian. Next we will be going to the implementation of mass Gaussian. So now I have implemented the mass Gaussian using a TensorFlow object detection API, not the direct on 2. So TensorFlow object detection API. So this TensorFlow object detection API was founded on 2017 by the Google. By the Google, the same year the mass Gaussian was being developed. So so what is the TensorFlow object detection API? That is the TFOD. So TensorFlow object detection. So this is the official GitHub repo of the TensorFlow object detection object detection API. So here you will be able to find the research folder, samples, officials, so license. So TensorFlow models, you'll be having the pre-trained models, research folds, or a large collection of models implemented in the TensorFlow by researchers. So in the research folder, you'll be having lot of models that has been implemented by the TensorFlow researchers. So if you move to an object detection, so if you move to the object detection, you'll be able to see the models, object detection models. So here you will be able to see fast touch inception V2, fast touch inception V1, SSD mobile net, SSD REST and you will be able to also see the configuration configs in the samples and configs you will be able to see. So this configuration is like same like in other algorithms other algorithms like in YOLO V3 or YOLO V2 also you'll be having the configuration. So when you are implementing the YOLO with the OpenCV deep neural network library OpenCV.dn and deep neural network library, you'll be giving the configuration and weights. So you'll be changing some configurations in that configuration file. When you're taking image size of large images, you'll be changing the input image size. You'll be changing some important things you'll be changing in that configuration. So here also you want to make some changes in the configuration. You want to change the path of the network, path of the input. You want to go the TF record path. You want to change the total number of classes. You want to change. You want to change the total number of predictions. All the things you want to change. So this is the configuration. So here you will be having the network architecture in this configuration field. So next, so this is all about the TensorFlow object dictionary. So you will be having all the important things. All you will be able to see. So anchor project generation you are having. So it's all been implemented. You will just use this implementation and you will be starting your training. Protos is the so Protos is just an Protos is nothing but than just a format of protocol buffer format where you want this is in a serialized format. You want to deserialize and you want to use this because as we are using Python, we cannot use this .proto format. You want to convert this to a .py format. You will be converting from proto to deserialize, and you will be converting that to .py format, and you will be using this Hankerbock evaluation. Also, you will be using fast CNN, hyperparameters. You will be using this after deserialization. So next, so there are also implementation of GAN also is there. Where is the GAN? See, GAN also is the General Adversarial Network. So they implemented GAN, they implemented the deep lab. Deep lab also is an semantic segmentation algorithm where it uses the conditioned random fields as a post processing, and was used and they saw an accuracy increase of 6 to 7% accuracy increase. They have seen deep speech also is there. So it is the official GitHub repo of the TensorFlow TF40 models. So now you will be cloning this. You'll be using this link. You will be cloning this official GitHub repo, and you will be utilizing this for the training. So this will be the TensorFlow object detection API. The next will be having you want to download a specific model you want to download, that is a mask Gaussian model. So if you move to an TF40 1.x, so this is a TF41 1.x model zoo. So here you will be able to see all the models, all the pre-trained models, SSD model, SSD mobile net, fast CNN model, ResNet 50, mask Gaussian. So here you will be able to see mask Gaussian instruction V2, Atras special pooling, mask Gaussian instruction V2 Coco, mask Gaussian ResNet Atras special pooling, mask Gaussian ResNet 50 101. So here you will be seeing the speed. You'll be having a huge speed of 470 fps and you're having the matrix of 33. So we are going to use TensorFlow 1.x, not the TensorFlow 2.x. In 2.x you will be having only one pre-trained network, that is the mask Gaussian insertion resonator. But in TF 1.x you are having 3 to 4 networks. Here they are having the pre-trained of CenterNet, efficient, it's a efficient design, which is maybe one of the favorite algorithm where they will be using a common skill and they'll be increasing the width, height, on the depth of the network with the available resources, and they have used a neural architecture source to find the efficient net, which uses the mp con for the efficient as a backbone. So next we then the ssd also is there. SSD mobile net also, SSD also has a high speed accuracy, high fps. learning rate. It also uses some concept of future permitting network. Intermediate predictions will be there. Non-maximal separation will be allocated. It also uses the smoothing L1 loss. Next, fast RCN also is there. Then extreme net is deprecated. So only there are three types of network. One is one star director like YOLO V1 V2, YOLO V2 V3 V4 on SSD. Then another one will be a two shot detector, that is the that is of fast RCNN, fast RCNN, mask RCNN, and the third one is the CentralNet family. Only three network are available. So now we have seen about the TensorFlow models. Next we will be moving into the preparation of the data. So now we want to prepare the data. So we want to collect the data. I'm going to use here the doc data set. I have collected all the doc data. There's 15 to 20 images I have collected, and I have annotated that using the label B tool. So this tool is also one of my favorite annotation tool, which you can use for annotation. So here you'll be able to see the notation. So here you'll be able to see all the installation. You can for using the Docker container. If you want to install, you can use this. If you want to use Anaconda command prompt. If you want to install, you can use this. If you want to use Ubuntu Linux based operating system, you can use this. If you want to use Mac OS, you can use this. For Windows, you can use this. So if you want, you can go with this installation. Or I have also mentioned the installation procedure here. Conda create. First, you will be creating virtual environment with Python 3.6. Then you will be activating that environment. You will be installing all the necessary things. Then you will be installing PyQt, PyQt library, which is used for the creation of the PyQt, where you will be using the PyQt 5 or Tinker also is there to create a GUI in for Windows or Ubuntu. If you want to create a GUI graphical user interface, you can use PyQt 5 or a Tinker also is there, that is also best. These are all the Python based library for creating a graphical GUI. Next, you want to install the label me and you want to type label me to access that in the Anaconda command prompt. Next, you will be this window will be popped up. Next, you want to choose the open directory. Then you want to go to a particular where the image is there, and you will be selecting that image. Then you will be click this create polygon boxes, start drawing polygons, create polygon boxes you want to create, and you want to annotate that. And after annotation, you'll be assigning a class, that is a label aeroplane you will be assigning, and you will be saving that. Now a corresponding JSON file also will be saved, where it will be having the height with where it will be having all the annotation points, all will be saved. That X and Y points all will be saved in the JSON file format. If you are using, this is the OCO based, so you'll be using JSON file format. There also XML file format also is there. So next, so I'll be showing the my annotation. So this is downloads mask CNN. So data. So I have annotated this training image. So I have annotated this 15 to training and testing. So I have annotated 15 to 20 images I have annotated, and see you will be able to see these are all the corresponding JSON file that has been created after my annotation. To annotation, this is for training and this is for testing. So when you are annotating, yeah, annotating for a corresponding image, that the JSON file will be created. Now you want to separate the JSON file and you want to create an training and testing folder. This was created manually by using the split folder library. I have created this folder. Training, testing I have created, and test.json, train.json must be kept in a different JSON file must be created in a different folder, and the JPG or PNG images must be kept in a different folder. So that can be achieved by using the split folder library. 18 to 20 ratio, you can split the images. Next, in the next you want to create a data folder. So this will be the structure of the creation. So you'll be having the data folder, then you'll be having the testing training.json, just.json, training images, testing images, then this will be the clear TF records. So as we are using the TensorFlow object detection API, you want to send the input data as a TF records. It will not be accepting JSON file or the JPG file. It will be accepting only the TF records. So you want to convert all the JSON files into one TF records. For that conversion, I have used the this create TF record.py file. This is the script file that has been written for the conversion. So this label map dog will be having the so if I show it will be having the ID and the class name. It will be having the ID and the class name. So item ID one and name is equal to dog. Then read pbdocs. These are all the helper file for the create TF records. This and this will be the helper file. This setup file is used for the to create object detection as a local package. You will be using the setup.py file. For when you are dealing with the direct on 2, that is a PyTorch based framework, you don't need to go this and all things. You don't need to convert to the TF records. You don't need to go, no need to have this label map. Directly you can go that Coco format, that is a JSON file format. Directly you will be able to go. So totally, I'm saying that more than TF40, Proton 2 is much preferable and easier. So the same thing I have written here. This will be the keeping your own training data. This and this. So I have also screenshot. I have also taken the script to. I have screenshotted it and I have pasted here. Then use of create.tf record as we are using TF40 framework for training mask casting. You have to convert all trainers on image into TF records. So we can use this create.script file for the conversion. And these are all with the helper file. Next setup.py file is used for the model. As we are following the model coded approach, we want to install the object detection as a local package. So this I will say or later you'll be able to understand when you are working on the training. I'll be showing this why you want to create object detection as an local package. Next label map.pbtxt that I have shown that. So this will be the sample. If you are having how many classes you are having, that much class also you want to mention all the classes here with a unique ID you want to mention. Next, you want to zip this folder. So I have zipped. I have kept all this. So see the structures, the same structure you must be following. So then after you will be zipping the data folder. So I have zipped the data folder. I have kept the ready. I have kept the data folder ready. So zipped and ready. Next we will be moving into the TF40 setup in the Google Colab. So I will open this. Opening. TF4. So if you like, you can follow this documentation. I have also mentioned all the step by step in the Google Colab also. So in the Google Colab also, I have mentioned see all the step I have mentioned step by step I have mentioned. If not, you can follow this also. This also step by step. The same thing only here in this document also. Same thing in that Google Colab also. It is the same thing. But in Google Colab, you are having the code. Here you are not having the code. Here only you are having the steps. So you have also the screenshotted the training data where you want to change the path, how you want to change test data, where you want to change the path, how to create, where you want to move the, what are the files you want to move, what you want to make the changes in the config files, what. So see here I also highlighted the changes that should be made by yourself. Next, what is the command for training? Then CKPT to PB conversion. So you can't use a checkpointing for the inferencing. You want to convert the model into .pb format, protocol buffer format. Next the structure. Now the prediction also I have mentioned. I have also shown the prediction, and I also made the conclusion. So we'll be seeing this later. Now we will be moving into the collab file. So in collab file, first you want to go to the runtime. Next you want to change the runtime type. It's GPU. If it is not a GPU, no problem. If it is a none, you want to. If it is a none, take select the GPU, save. It has been connect. So it is allocating. Connecting, initializing, should show connected. So now you mount your Google Drive. Will be Google Drive as a local storage and will be performing our training. So connect to Google Drive. Use your own Google account, Drive account. Allow go all the things allow. Next, now your Google Drive will be mounted. So it is taking some time for the mounting of the Google Drive. So the Google Drive has been mounted. Now we are creating an root directory that mask ASEAN and training. You are creating a directory in the Google Drive. So I'll be, if you see, so I have created the mask ASEAN and training. Now I am moving into the CD. This is a Linux command. So as Google Colab uses the backend as Linux, so we are using the Linux command and we are moving into the Mask training. Now we want to download this repo. So we'll be using this repo, and using this repo only you'll be able to make training, because all the implementation, all the anchor box generation, all the training evaluations, all the implementation are available in this TensorFlow official GitHub repo. So you want to clone this official GitHub repo and you want to use this for the training. Use you want to configure something and you want to use this. So you'll be cloning this GitHub repo. So it is getting cloned. So it will take some time, 10 to 20 seconds it will be taking. Next, you want to download the mask ASEAN pre-trained model. So the pre-trained model. So I'll be mentioning that Word file also I have mentioned. So if you see here, yeah, you want to download this mask ASEAN Inception V2 Coco pre-trained model. If you click this, it will be started automatically will be started downloading. So I will be showing that. So see here, it is getting started downloaded. It is something 170 MB. So now I am moving this, not required. So this model will be downloaded. This is a pre-trained model. Pre-trained model. So so your now the cloning has been done successfully. Next, you want to download the model. So paste the link on wget function. Using the wget, you will be able to download the model. So I have downloaded. It is something 170.58 MB. Next, you want to this will be in a tar file format. Now you want to extract this tar file format, unzip it. So now I will be unzipping this tar file. After unzipping, I'll be changing the name. So if you see here, you'll be able to, this is for my convenience, I am changing this name. So it is like mask ASEAN session v2 blah blah blah. So it is having many, the name is too huge, so I'm changing that to a mask ASEAN by using the mv command. I'm changing that. So now it will be, now this command has been changed. Now this name has been changed into mask Arsian. If you refresh, you will be able to see the photo name has been changed into mask Arsian, and you will be able to remove the zip file. I know the tar file, so I will be removing this. Now, if you see here in the mask Arsian folder, so this will be all the checkpoints. So this is the main, this will be your model, that the .bb model. This will be your pre-trained model. You will be using this model. You will be retraining this model again according to your data, and you will be using that. So these are all unwanted. These are all checkpoints. So you don't need this. We need only this PB format. So in TF4, no, mainly we need the pre-trained model. Next, you want to make changes in the configuration file. Next, you want to move some .pv files like train.py. You want to move to a research folder, that is a root folder, and you will be starting the training. Mainly config file changes you want to make. You want to convert your data into .tf record, and you need a pre-trained model. So it is, so I'm using 10 dot tensorflow.1.x. So I'm making tensorflow.1.x as an backend. And then these are all the some requirements: the pillow library, XML, Jupyter, Matplotlib. These are for visualization. OpenSea also is for visualization and for image processing. I'm installing all the requirements, so it is already has been installed. Next, I have said the research folder will be your root folder. So if you are going models, research, so this research folder only will be your root folder. From here only we will be training our network. So we are moving. I'm moving into the research folder. Now the important part comes. That is the protos. So the protos I'll be showing here. It will be very easy. So research, now the proto format, that is the object detection in the protos. So if you see here, all the implemented, these are all the implemented made by the TensorFlow team in the Python language, but they have converted that to a dot proto to these are converted to dot proto format to share that file. Share that file. So it has been serialized. Serialized. Now we want to deserialize this proto format into dot py format, and we want to use this. So this they have done to share the things much faster. Serialization and deserialization. How we are doing unzipping, zipping and unzipping. Still make serialization and deserialization. Now we are doing a deserialization. So if you see here, object detection. Next, you will be going to the protos. If you see here, all the models are in dot, all the implemented necessary implementations are in dot proto format. Now, if I once I run this, then all will be converted into dot py format. So now I'm running this. So now, if you refresh this, you'll be able to see the for corresponding photo, you'll be having corresponding py file format. So here, see here. Now the .py file format has been created. Now you can use this .py file format and you can make the implementation. So box predictor, some center net, some evaluation. So evaluation also you can use these files. Then we are coming back to the mask RCN and training photo. Next the important part comes that the conversion of the uploading the data folder and conversion into a TF records. You want to upload the data folder. So this is a special code for the uploading the folders in the, you can upload only the folder in zip file format. You can't upload the direct folders, and you can upload the files. For while you are using Google Colab, you can use this code and you will be able to upload the folders and files much easier. Or you want to choose this upload section storage, then you want to again you want to click this and you want to again upload. Or that you can use this command and you will be able to upload easily. So it is taking some time, 10 to 20 seconds it will be taking. 72% done, 76% done, 80% done. So next here is the unzipping process. So you will be the data.zip you will be convert you will be unzipping it. So now I will be unzipping the it will be in the GIF format. I will be I want to unzip. If you see here, if you refresh and if you see here, you'll be having the data.zip. Now I want to unzip it. So run this cell. Now that the .zip has been unzipped, if you refresh, you'll be able to see the data folder and all the necessary requirements, all that testing and training data, annotated JSON files, all will be available here. Now you can remove this .zip file. As we know it, the zip file, you can remove this. Next, convert .json to .tf records, and now we want to create the tf records. So now we will be, as I said, we will be using the create tf record.py file, and you will be making the conversion. You want to change some paths in the tf in the create tf records. So run this code. Your tf create tf dot records create tf.records file will be open. Move to the last. So here I have given the train image path. So here you want to change the path related to your path where the training and testing data are available and altered data are available. So this path I am already configured. I want to make only the changes in this line. This should not be test. This should be train. And the content mass Gaussian data training. So if you see the path, this will be the same path, content mass Gaussian and training. So it will data folder and it is a training. Now this is the train image path, train JSON path, label map path. You want to go the label map path also, and you can save this file. This is only for the training data set. Again for the testing data set, you want to do again. So it's saved. Now you are now run this command. You run this .py file. That is a create record py file using Python. You will be running now. You will be create here. You will be the tf.record file will be created. If you refresh, .record file will be created. See here, custom train dog record file has been created. Next, same this thing you want to perform for the test.json and testing. So open this file. Come to the last path. Here you want to change the data or training, you want to change into testing, testing. Next you will be using test.json. So test.json label map, this will be the same. Next you want to for train, you want to change it to validation. Save, close. Next, run this command. You will be able to see the dot custom val dot record will be created. Refresh, custom val dot record will be created. Now, as I said, the result for research folder will be your root folder. You want to move all the necessary folders into the research folder. So now we know it, this training, testing, that all we know it. We need only the dot record files. So we'll be moving that record files into the research folder, and the setup.py file also will be moving into the research folder. So run this cell, all the setup.py file, all the things will be moved. Now setup.py file will not be visible here. If you refresh, this will not see all the tier dot records and the setup.py file will be moved to the models research and setup.py file. See here. That's setup.4. So next we want to install the setup.py file. As I said, the object, you want to make the object detection as an local package. So this is the object detection. You want to make this object detection as local package. You want to write a setup.py file. You want to mention all the requirements that should be installed, all the versions, name, all the things you want to mention, and you want to install the setup.py file. So pipin, you're going to use Python model install pfl install you can go, or you can use this pip command and also you will be able to install this. So this hyphen e and this dot is to install the setup.pfl. This dot will be saying the current directory. Next we have installed all the setup.pfl. Next our process is to make the training. Now we want to start the training. For starting the training, the main requirement is to change the config file. I have already said that you want to make some changes in the config file. So this the config file is available in this path. So this will be the configuration file. This will be the configuration file. So you want to copy this configuration file to the training folder. So before that, you want to create a training folder in the research directory. So research directory will be a root directory. So in the research, you'll be creating a folder called training. If you are refreshing this, you'll be able to see the, so training folder has been created. Now you want to, in the training folder will be considering the label map. It will be considering, so your training folder will be having the label map dot.pbtxt will be having, and it will be having the configuration, and all the logs will be stored in the training folder. All the checkpoints and the logs will be stored in the training folder. Now we are copying the, now you want to copy the label map to the training folder. You want to copy the configuration to the training folder, and you are copying the mask RCN, and you are moving the mask RCN folder, that is a pre-trained model folder, into the research folder, because research folder will be your root directory. Next changes to be made in the configuration. So now we want to make some changes in the configuration folder. So what are all the changes? If you want, you can see here, or you can also visualize the changes that should be made using this PDF important document. I'll be mentioning here all the changes. So here you want to change, all the changes will be mentioned here. If you follow this, you can follow this documentation. You can change, or here also I have mentioned in the Google Colab also I have mentioned. So the classes must be not 90, should be one, because I'm using only one classes, that the dog classes. So minimum dimension, maximum, I no need to change anything. Scales, aspect ratio, this is all I no need to change. This is a anchor boxes generation. They'll be using the scales and aspect ratios. Next threshold, I no need to change. This is a max pooling. Max pooling also I no need to change. Next, you want to move to the 127 index of 127. So learning rate, they're using some 0.0002 small learning rate they're using. So we can get a better training result. So next 127 here you want to go the fine tune checkpoint, that is the pre-trained model CKPT point you want to go. So my pre-trained model CKPT point will be in the mask RCN folder, that will be the model.ckpt. So I want to go this path. So it is a mask RCN, so we'll be little minimizing this. So CKPT. So copy this and paste it here. I have pasted the fine tuning checkpoint. Next, number of steps. So number of steps is like number of epochs. I'm not going to train it for 20,000. I'm going to only train it for I'm not going to train it. I'm not going to train it for this much number of steps. I'm only going to train it for 2,000 steps. Not going. It is number of steps is like 2 lakh steps. It has been written, but I'm going to train only for the 2,000 because for 2 lakh steps I cannot train this Google Colab. It will be crashed as it is only a normal version. If you have Pro or Pro Plus, you can use that and you can train, but it is a normal only it is possible to 2000 to 5000 number of steps only I can able to run. If it is 2 lakh steps, then but your result will be very 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 good if you're training for the huge number of steps. Now next you want to change the input. Next we have came for the input. Now you want to change the input path. This is your input, that is tf record. Create train tf record path you want to change. This is the tf record input path I want to change. The that is the custom train dog dot record you want to do. This is the training annotated image that has been converted from JSON to TF dot records. Next you want to go the label map part, that is the training. It is in the training folder, label map dot pbtxt. These are all changes has been taken place from the research folder. So you should be in the research folder, otherwise you cannot run this. Next, you want to again for the testing also, for testing image also you are converted into JSON file. The same thing here, you want to change the TF dot record for the testing, you want to change here. So here you will be having the testing. You want to change the testing path. Change the path. Next, you want to change the label map pbtxt, that is in the training folder. .pbtxt. Copy this. Make the save now. Save the we have made all the changes. Save this config file and close this config file. Save this config file, close this config file. Now you want to now you want to copy the train.py file. So we will be using this train.py file and we will be training. This train.py file will be in the object detection folder, will be in the legacy folder, and you'll be having the train.py file. If you open the train.py file, now you will be able to see that it is following the modular coder approach where object detection is taken as an package. If you are not installing the object detection as a local package by using the setup.py file, here it will be throwing the error. So you want to create a setup.py file and you want to install that. Otherwise, here it will be throwing the error. So now you want to copy this train.py file from the legacy folder and you want to paste it in the research folder. Research will be a root directory. Again, you want to copy the deployment and nets. So deployments and nets, when the deployments and nets also is an important files or folders that must be pasted in the research folder. If you want to research, you go to Slim, you'll be having a folder named Slim object reduction. Slim will be having the deployments and nets. So deployments and nets, you want to copy this. So you in deployments and nets, you'll be having the required.py file. So these are all the PY file that has been required. So you'll be having all the backbone networks here. So you want to copy this deployments and nets and you want to paste this in a research folder. So run this command, you'll be copying and you will be pasting in the research folder. So all this thing will be pasted, will be copied and pasted in the research folder. Now if you refresh, I have refreshed, so I'm in research folder, you'll be able to see the nets has came, deployments has train.py file has been arrived. Next deployment alone was deployment also has been arrived. Deployment folder. Now these are all some dependencies that must be installed before the training. Here of Slim and NumPy. So now this will be getting installed. So after this installation, next you want to use this command for the training. It is the Python Python trained now this has some pip error is coming. No problem. You don't want to take care of this. Now you can go with the training. That is the Python train.py. So you'll be using this train.py file. Next log directory where the log should be stored. Log should be stored in this training folder. Next, your config also is in the training folder. That is the config. So I'll be saying the folder structure. So first you want to have this training folder. In this training folder, you'll be having the label map pbtxt file that is used for will be containing the classes and the ID of the classes. Next, it will be having the mask RCN where you will be having mask RCN config files. So this config file is very important for the training. If there is no config file, you can't start the training. Next you want to have the mask RCN folder that will be having the pre-trained models. Using this pre-trained model, you will be training, and all the logs will be stored in this training folder. And the train.py file that is copied from the object direction legacy folder, and it has been pasted in the train.py file in the research folder. So now, if you run this command, you will be able to see your training will be started. It is at 2000 steps. It will be training. So there is some logs is coming, some call function. Then your input images will be read successfully. It has been read. Tensors. We are using tf1.x for our training. So you want to mention all the graphs. In tf2.x, you don't need to mention the graphs, but here the graphs are important. tf1.x. So your training is going on. So it's going on. So now you'll be able to see the steps. Steps on step one, the loss is this much. On step two, step three, step four, that is the epoch one, epoch two, epoch three, epoch four, epoch five. Your loss is this much. Now the training is getting started. Now it will be the training for the 20,000 steps, 2,000, not 20,000. It will be training for 2,000 steps, and we can start. We will be converting the model CKPT into PB conversion. All the logs will be stored in the training. Now, while opening C, now all the checkpoint is getting stored. Not here, training. Before this execution of the command, you was having only the label map.pbtxt and you are having the config file, but now you will be able to see all the checkpointing has been generated, all the logs has been stored here. Now you want to convert the CKPT to PB conversion, then we can start the prediction, that is the inferencing part. So we can wait for some time. It will be taking some around, it will be taking 40 to around 20 to 25, 35, 20 to 25 minutes it will be taking. After this training, I'll be explaining the prediction part. Thank you. Okay, now we'll resume our discussion. The training has been completed. It has taken around 10 to 15 minutes for the training up to the 2000 step. For only, I have used only 20 data set with two validation data set. It has taken 10 to 15 minutes. If I use huge number of data set like some 2000 data set, some 1 lakh data set, some for around 2 lakh or 3 lakh steps. If I use it, will be taking huge number of time. It will be taking around maximum. It will be taking around 5 to 6 hours of timing. So this is the summary. Next, we will be converting now. The training, I have said that in the training, all the logs will be stored. Now all the logs has been stored here. Now you want to convert the CKPT to PB conversion. So the checkpointing directly we can't use checkpointing file for the checkpointing. Sorry, there was some fan sound, so I am off. Turn off that. Now we want to convert the CKPT to PB conversion. We can't use the CKPT for the inferencing. We want to convert that to an protocol buffer, that is the PB format. For that conversion, I have to copy an export inference graph that will be in the research object detection folder. You'll be having export inference graph. So object detection will be here. Here you will be having the export and inference zone. So all the implementation are available in this repo. You want to just copy and paste in research folder, and you have to make use of that implementation. Now I will be copying that export inference app and I will be pasting in the research folder. So it is copying and it has been pasted. Now I want to export this. So this is the command for the exporting of the inference graph. Here you want to make one change. That the change is that you want to change the this CKPT number. So this number will be related to a checkpointing number. That is the latest checkpointing number. You see in the training folder, your 2000 will be your latest checkpoint number. So you have to use the 2000. You have to do the 2000 here. You can't go the 1000. You want to go 2000. So 2000 is your latest checkpoint number. You can go either you can go 2000 or you can go 1252. Only this two number you can do 1252 and 2000. You can't go 1000. So next, now you have provided the latest checkpoint number. Now you can start the training. So the inference graph will be the output directory. The inference graph will be created in the frozen inference graphs. On the research folder, a frozen inference graph directory will be created. Inside this inference graph will be .pb file will be created. So if I am running this, you will be able to see the frozen inference graph folder will be created here. Inside that frozen inference.pb file will be created. So research, now it is taking some time. It is now it has been created the it has finished the conversion. Now if you see the load this, now you will be able to see the folder frozen inference graph. Inside that you will be able to see the frozen graph.pb model. So this will be your trained model, retrained model. Now you will be using this trained PB model and you will be inferencing this. So training has completed successfully and model has been saved in the research frozen inference graph. Utilize that model for the inferencing. We'll be using this model for the inferencing. Now this is the prediction. This implementation also available in the this implementation also is available in the GitHub repo, TensorFlow GitHub repo. Now download the import the necessary packages. You TensorFlow now strict version. Next you if the strict version is less than 1.x, if it is then only if strict version is less than 1.90, then you go and please install the version greater than 1.90. So these are all the necessary import you will be importing. So after importation, after importing the libraries, next these are also necessary in the imports. So after this import, imports, next you want to give the model path. That is the path to the frozen inference graph. So that will be the path to the frozen inference graph. This path you want to go this relative path here. So I have already given the correct path. Next, you want to go the path to the labels. That will be in the training. Where is the training? Then this label map.pbtxt, the label map.pbtxt. So it is in the training label map.pbtxt folder. Now run this code. Next, you want to load the frozen inference graph. Now you want to load this frozen inference graph.pb. As we are using TensorFlow 1.x, you will be using the tf graph. You'll be using this tf graph function, and you will be loading the pb. That is the frozen inference graph. So if you want to visualize the frozen inference graph, you can use the Netron. You can use Netron, and you will be able to. You'll be able to. I have not installed Netron. You can use this Netron, and you will be able to visualize the frozen inference graph. If I show you, if I want to visualize, so we open with Netron. See here, the Netron is there. So it will be taking some time, I think so. Model will be very huge model, so it will be taking some time. So you can use this Netron and you can visualize all the things. You can visualize all the layers. You can see the weights. You can see the bias. By this, we can conclude that the neural network or deep learning is not a black box. You'll be able to visualize all the things. See here, you'll be able to see all the layers. What are all the layers? Where the skip connection is happening? Where the concatenation is happening? Where the RPN proposal also happening, where future proof network is used, where the concatenation is happening. All things you will be seeing the convolution 2D type. If you click this, you will be able to see all the inputs, padding, what is the padding, same padding or valid padding, all straights, what they have used, inputs, outputs, all the things you will be able to visualize, and you will be able to visualize the weights also. So you can get the help of Netron, and you will be able to see all the visualizations. So next you load so I think we have read this model. Next you want to load the PB level map path to level map.pbc by using this. And next this is a helper code. This is used to convert the image into numpy array. And then now we want to upload the training images. They are not training, it is a testing images. We have trained, we have validated, now we want to upload the testing images. So I have around 10 testing images. Now we will be able to visualize that result for the test image. So open this. So it will be taking some times into some 20 seconds. 65, 87, 100. It has been uploaded. Now unzip it. If you see here, it will be in research only. If you have uploaded in research, if you see here, then you will be able to see the test test image. You will be able to see it. You'll be able to see 10 test images. And the main thing is that the test image must be named in this order: image 1, image 2, image 3, image 4, image 5, image 6. Because this is done because to access the image easily, because here you by this piece of code you'll be able to access the image easily. So here you'll be having the image name, and here we have written a for loop and iterating. So image 1.jpg, image 2.jpg. Here they are using string formatting. They are using the string formatting, and here you'll be get this in this dictionary. You'll be the value will be replaced for so image 1.jpg, image 2.jpg, image 3.jpg, and here you are having the voice the path join. You'll be joining the path to the image directory and the image, and you'll be able to easily access or read the images. So this will be the path to the images. This is will be the path or the directory of the images where that has been stored. So image must be named, testing image must be named in this order: image 1.jpg, image 2.jpg. This is an important thing. Next it's a visualization. Simply run this code. You'll be able to see the number of detection classes, detection boxes. So in TF, only in TF you can see that this number of detection. You can fine tune this number of detection. So defaultly it will be 100 detection per class. So per class only it will be able to detect 100 detection. So if you want, you can increase this. Only it is available in the TF40. Total 4 outputs will be coming. There is a number of detection classes, detection mark, boxes, scores, and masks. 2, 3, 4, 5 outputs will be coming. Next is the visualization part. Now run this. It will be taking around 10 to around 1 minute or around 1 to 1.5 minutes for execution of this code. So by I'm using 20 only 20 training data set with only 20,000 2,000 steps. So now we will be able to visualize this. Only 2,000 steps with only 20 data sets. So it has been. So you'll be able to see the result. The result is pretty much good. It was pretty much good because by using only 20 data set with only training of 2,000 steps, you will be able to see that you are getting a pretty good prediction. So dog it is classifying 100%. Here it is classifying as 100% dog. Here it is classifying 100% dog. The mask also has been correctly segmented. Here there is some overlapping. We want to increase the steps. We want to increase the data. Then only this overlapping. All this will be removed. So here it is pretty good. It has been detected the mask and the bounding boxes. Here also it was pretty much good. Here also it is pretty much good. Here also it is correctly directing. Here also it is correctly directing. So here also, so I'm testing for 10 different dog data set. It is pretty much good for the it is pretty much good, it has given pretty much good result. I have trained only 2000 steps with only 15 data set. The result which I am seeing is pretty much good. So by this we can come to a conclusion that if you increase the amount of data set from 20, if you move to 2000 or 2 lakh data set, you can increase the accuracy, and you want to go huge number of, and you want to increase the steps. For that you should not go higher, more higher steps, and more you should not go more. Then there will be some overfitting may happen and your model may collapse. So for that, and it will be taking a lot of time. So you want to go and at least some minimum, at least minimum 10,000 to 20,000 data sets, and at minimum you want to do 2 lakh to 5 lakh steps. Then only you can see a pretty good result. When you are making an application, you want to, when you are making an production based application, you want to increase the steps and you want to go pretty good. That is, then only you will be able to see a good result. So by this we can conclude. So this is the you. So we have visualized all the deduction. We have trained our data set. We have also seen the inferencing. So we have got a pretty good inferencing. So now I will be concluding this project by saying the conclusion that I have said that you should increase the steps, and you want to increase the image, you want to increase the images, and you want to increase the steps. And the main thing is the data argumentation and data annotation. Data annotation must be done perfectly. If the data annotation is not done in perfect manner, then your the mask that is getting generated will not be good, accuracy will not be that much good. And the data argumentation, you have to do data augmentation to be more, to make a model more generalized. It should not be focusing only on the particular shape or particular size of the object. It must be focusing when angle changes, when the brightness changes, when the image changes, when the angle, size, image, all it changes, your model must be able to detect or segment them. For that, you want to do one data augmentation. For data augmentation, you can use Argumento, Argumentation. V7 Lab is there. That is online data augmentation tool. For annotation, also you can use V7 Lab. You can use Label Me, Label IMG for the bounding box generation. Label Me for the later segmentation. You can use V7 Labs, and and you can use, also you can use Amazon. In cloud also you're having, in cloud also you will be able to get the annotation tools like AWS also you can use the tools. And there are different, and there are also paid tools for the annotation. So data argumentation and annotation must be done very carefully. So this is my summary. And data annotation and argumentation must be done very carefully. Then only you will be able to get a pretty good result. So by this I will be concluding my project. So thank you.